The Einstein theorem, generally theory of gravity, this talk is for you. You're welcome.
The border between physics and mathematics is not always very clear, but roughly speaking, if physics is writing equations and mathematics is solving them, which is not always true, then this talk will be rather in physics than in mathematics. And although there will be some mathematical structures presented here, which I believe are relatively easy to understand.
Przepraszam bardzo, da się coś z dźwiękiem zrobić, to jest średni.
But what we know about gravity is we know it from small scale. I mean small with respect to the size of the universe, because of course the interplanetary scale is extremely big for us, but as far as the cosmology is concerned, it is nothing. It is very small portion of the universe. And co zrobić?
Okay.
And in principle, try to extrapolate our knowledge, which is understood.
Jest jeszcze gorzej.
Panowie, z głosem coś jest nie tak.
Has been accumulated this way, that we know something and we try to extrapolate, and if it doesn't work, then we try to find some corrections. But in principle, this anthropomorphic point of view is prevalent in also in contemporary physics. But extrapolating something by 20 orders of magnitude, I'm sure that it will not work. And this is what we try to do when trying to apply the present state of general relativity to cosmology. This is just extrapolating by 20 degrees of orders of magnitude. We know that, for instance, extrapolating classical physics to atomic physics, which is only 8 orders of magnitude, doesn't work. Because from centimeter to angstrom, there is 8 orders of magnitude, but between solar system and the cosmos, at least the cosmos as we understand now, is almost 20 orders of magnitude. Therefore, probably we should try to understand better the origin of the present state of general relativity. When I am very, very tired, in the evening, I read a book, a collection of the so-called philosophical papers by Albert Einstein, which is a collection of his a little bit less mathematical papers, which he presents his way of thinking at the very beginning. And I was always very much struck by the fact that there is a jump because at the very beginning, Einstein was always thinking about inertial frames. And of course, we know the story about free-falling elevators and so on and so on. But the mathematics he was used was very much different, namely the Riemannian or pseudo-Riemannian. At the beginning, it was Riemannian, then it was somehow improved by Hermann Minkowski. So let me begin with the origin. Here no, doesn't work. Well, yeah, so I will probably skip few, this is what I have already told you. So let us re-examine the meaning of general relativity theory. Everybody knows that this is the original Hilbert Lagrangian. Then Einstein, for some reasons, introduced the so-called cosmological constant, but later on he was very much unhappy with that. Then there was different, for instance, tak. To niech pan przesunie jeszcze. Tak, yeah. This correction, which nowadays is very well known by astrophysicists and people who are doing astronomy under a different name, this correction was first introduced by Andrei Sakharov in '67, but the reasons were more mainly related with an attempt to quantize, say, quantization of. No i co? Ojej, znów mi nie chce działać. Nie działa. To co mam zrobić? Co? No nie, no bo nie przez. Działa, dobrze, przepraszam bardzo. Nowadays there are many generalizations of general relativity which are based on such a Lagrangian, where R means scalar curvature. Also such more general theories where the Lagrangian is allowed to depend upon the entire curvature, tensor, and so on. But let us go back to the origin. So if no gravity, then our physics is based on the Newton's first law, which tells that there is an inertial frame. What does it mean? It means that there are bodies which are not subject to any forces exhibit rectilinear motion with constant velocity, which means that there are coordinates such that this they fulfill this equation. This statement, when analyzed carefully, means nothing but the equations of motion are of second differential order. So the Newton's first law may be formulated this way. Equations of motion are of second differential order. Whenever they are of second differential order, then there exists such a system of coordinates that they look like that. Equations of second differential order are carry an interesting mathematical structure, which is very simple, and I am going to tell you this story. Yeah.
What about the fact that frame of reference which moves with constant velocity with respect to an inertial or the frame of reference is also inertial?
Yeah. If you perform a linear transformation of coordinates, it will this equation remains valid. Yeah. I don't claim that the inertial system is unique, and I will go in details. Wait a moment. By the way, suppose that we are now around 1905 or something like that, or no, 1910, say, 10, just after the discovery of special relativity. Therefore, we already know that the time and space have to be combined together. So from the very beginning, I will use not space coordinates, but space-time coordinates. But of course, you may ask, so what are these dots? Dots with respect to what? Because in classical Newtonian physics, there were space coordinates, and dot meant the derivative with respect to time. So this dot is some internal time. So, for instance, suppose we are in a spaceship far away from our planet, and we are equipped with a good clock, for instance, a biological clock. Yeah, we are getting older and older. When you are young, you don't feel that, but I have a strong feeling that this biological clock works perfectly. So and this is a derivative with respect to that clock. Of course, which unit of time you use, seconds or years or something like that, it doesn't matter here. Yeah. Newton meant that his statement, there is an inertial reference frame, meant that this reference frame is global. But at that time, 17th and 18th century, people were thinking that the cosmos is small, relatively small. At that time, when you read the estimates, how big is cosmos, it is ridiculous with respect to what we observe now. So, difference between local and global is that the Earth is also flat in small scale, yeah? The president of Warsaw, when planning the development of the city, never uses spherical geometry, yeah? The angles in a triangle is, the sum of angles in the triangle is always 180 degrees, precisely. We begin to feel that something is on, that some description is only local and not global, only in bigger scale. So take another coordinate system, which is no longer global, and try to rewrite this equation in this not necessarily inertial coordinate system. So the first derivative, then the second derivative, we treat those y's, inertial coordinates, will always be described by the letter y today. So we consider y's as being functions of those x's. So we just take second derivative. And now, if both y's and x's are coordinates, then it means that this matrix is reversible. Therefore, we may apply the inverse matrix and calculate this way. So we see that the fact that acceleration vanishes in a non-inertial system doesn't mean that the second derivative vanishes. Yeah, it means that such a quantity vanishes. Now, the coordinate system X is also inertial if the matrix of second derivatives of y's with respect to this new coordinate system vanishes. Then again, X is a coordinate system. Otherwise, not. So this relation leads to the following mathematical construction. Let us consider an equivalence relation between two coordinate systems. At the moment, everything is global. Everything is global because, following Newton, we think that the universe is small. When we choose a coordinate system, it is probably good for the entire, but only for a while. So, two global coordinate systems in space-time, we will consider them as equivalent if and only if the matrix of second derivatives vanishes. At the first glance, it doesn't look as a equivalence relation because I think you all were well trained in mathematics and know that this relation should be symmetric, whereas here apparently it is not, because y's are up, but because of the zero, in fact, it is very easy to prove that this relation is symmetric, and so on and so on. So it is a genuine equivalence relation. Therefore, what is inertial reference frame? It is not just a coordinate system, but it is a class of equivalent coordinate systems. So what I have told you is trivial from the mathematical point of view. So when there is no gravity, it means, because such a global reference frame, existence of such a global reference frame means nothing less, nothing more than an affine structure of space-time. Yeah, what is affine structure? The absolute teleparallelism with zero curvature, roughly speaking. So each of those representatives of such a class imply this teleparallelism, and it is a priori flat. Now it is worthwhile to denote by gamma lambda mu such a combination of derivatives, where I remind you from the very beginning we know that those y's are inertial. Yeah. So this means that the motion in the free motion in may be described in non-inertial frame this way. Yeah. Of course, we may multiply everything by the mass, and then this is just a Newton's law, the second Newton's law, and this combination of derivatives we may call inertial forces. This is a very good language, and for instance, tak, zdejmij, bo jak mówisz w masce, to ja nie.
Equivalence relation.
Yeah.
Suppose I have crazy coordinate system, which is not inertial.
Yeah.
And I take all linear transformations.
Yeah. They will belong to this class.
So this class does not represent inertial frame. Yeah? So if I want the inertial frame is one of these classes. So before we, and a reference frame, each of these classes may be called a reference frame. Now, the God or somebody else have chosen one of these classes, and he told us, oh, this one is an inertial frame. The others are not. But he is free to choose one of them, because after speaking, they all are equally good. But he has chosen one, and he told us this is an inertial frame.
Yes, so this is my question. Because this construction is, of course, very nice, but if you want to do some physics, you really need to have an operational definition of what inertial frame is. You assume that there is an inertial frame, but you never tell me what this inertial frame really is. And
No, you just try to, you observe the motion of free bodies, and you just try to find a system in which the second derivative is equal 0. By the way, when I was teaching children of the second academic year classical mechanics, so there is a chapter devoted to those fictitious forces, centrifugal, Coriolis, and so on. So these are those. And this language is also pedagogically very useful, but just a side remark. Yeah, and now gravitation. So gravitation begins when we admit that the universe is big. It's not such a small that everything may be considered global, but it is big enough to see the difference between things which are local and global. So in gravitation, we have something which I have a tendency to call not Newton's, but Einstein's first law, which says there is an inertial frame. Everywhere there is an inertial frame, but only local, at each space-time point separately. And maybe there is no global inertial frame. So what is, an inertial coordinates are such
that, again, the same like in Newton geometry, Newton's physics, there are such coordinates that the freely falling bodies obey locally, but locally only at this point, because already in a neighborhood, these coordinates probably are already not inertial. Which simply, and this statement means nothing more, nothing less, that the equations of motion are of the second differential order. Take another coordinate, we may perform the same calculation, which is really trivial, but now everything is local. So let us introduce again the equivalence relation between different coordinate systems, but local coordinates, and this equivalence relations carries the name of the point. So there are as many equivalence relations as there are points of the space-time. So two local coordinate systems in a neighborhood of a point M is just a space-time point, are equivalent if and only if those second derivatives vanish, but at this very point and not necessarily in a neighborhood.
Excuse me, may I have a question, please? May I have a question, please?
Who is talking?
Piechocki, Włodzimierz Piechocki.
From the speaker. Yes, from the speaker.
So, can I continue, please?
Yes, you may continue.
Yeah, continue.
Yes, you can't define derivative just at the point. You need neighborhood of a point, okay?
No.
Jacku, zrozumiałeś? To mi przetłumacz.
Można w punkcie liczyć pochodną. No,
Co?
można.
Co?
Można. You may derive derivative at point.
Yeah, at point. Yeah, derivatives should vanish at a point. And again, it is a very easy task, first year mathematical analysis, to show that this is indeed an equivalence relation.
Shouldn't the left-hand side, by the way, shouldn't the left-hand side have x lambda of n rather than n of x lambda? It's not
Yeah, of course, in this notation means that y's are considered as functions of x's. However, if this vanishes, then if you invert this dependence, then again the second derivatives of x's with respect to y's will vanish. This is really an easy exercise. So it is indeed, moreover, equivalence relation should be reflexive and transitive, and it is easy to prove. Therefore, it is a genuine equivalence relation, which simply means that when we choose a point in space-time, all local coordinate system in a neighborhood of M split into equivalence classes. And each of those classes may be called a reference frame, Until now, there is no physics. It is a reference frame. And now what is gravitational field? Gravitational field is nothing but the field of those inertial frames. This means that if we are living there, at each point of space-time, there is a privileged class or a privileged reference system, which is inertial. Why it is inertial? We will try to understand it later, but at this point we can say God has chosen this particular reference frame and he called it inertial. And he did it at every point of space-time separately. So in physics, whenever we have a collection of geometric objects at each point separately, we call it a field. So we may say that gravitational gravity is a field of local inertial frames.
Right.
At least I claim it. You may not agree, but let me continue. Yeah.
Well, the question is indeed why this assumption is extremely strong. This is essentially the assumption.
It is not. It is, no, it is not. In fact, what you are doing in a standard gravity is that. However, this point of view is better because you have more perspective, I would say. But roughly, you will show. This is.
Let me phrase my question differently.
Yeah.
So suppose you want to construct geometry, say generalization of Riemannian geometry, in which you don't have a tangent space concept at all. Is it possible?
I have what?
No concept of tangent space.
No, everything we assume from the very beginning that space-time is a differential manifold. Therefore, tangent space is a priori given. Jacek?
My question is, by gravity, you mean action of gravitation on bodies.
Yeah,
Not
wait a moment. Of course. This is an extremely important point, which I'm going to discuss in a sequel. Okay.
So for instance, in my world, there are only this object, this charge. And in my world, there is also magnetic field everywhere.
This is only magnetic, electromagnetic field is something else. At the moment, I am discussing only a gravitational field.
No, I mean by your definition. So by your definition, now this magnetic field also becomes part of this gravity, right?
No, at the moment, no.
No, because if a charge, so for instance, a charge in this magnetic field, so it's like drop freely. So it will defect.
No, if there is a magnetic field there, the motion will be. Okay, please wait a moment. I will come to that part. Okay, so now, whenever we have a field of geometric objects, then mathematically, those of you who are a little bit trained mathematically, you know that we very often want to consider the collection of all possible such objects, and then the field, that means that at each point we choose one of them, can be treated as a section in a certain fiber bundle. Yeah. So, and really, let me discuss this shortly, that the collection of all these reference frames constitutes a nice fiber bundle over space-time. So given a coordinate system in a neighborhood M, any other reference frame at this point can be uniquely parameterized by the following table of numbers. So, because at the beginning, those classes look very abstract. There are equivalence classes of coordinate systems, but in fact, this is a very simple mathematical structure. whenever we have two coordinate systems, then there is such a table of numbers in space-time, for instance, which is four-dimensional. This means that we have 40 numbers. Why 40? Because this is a priori symmetric, just from the definition, because this is second, yeah? So there are 10 symmetric matrices in 4 dimensions times 4 arbitrary upper values of the upper coordinate, therefore 40 numbers. Whenever I have, so if I choose this X as a single point in this collection of all reference frame, then whenever I have another one, it may be parameterized by those 40 numbers. Therefore, the bundle, a singular bundle, is 40-dimensional in 4 dimensions. Of course, it depends upon them. And this parameterization is good, which means that whenever you give me such 40 numbers, I find uniquely this reference frame. Of course, I don't find uniquely these coordinates, but the equivalence class of those coordinate system may be found uniquely. Therefore, we may this quantity does not depend upon the choice of a representative y, and also does not depend upon the choice of coordinates x within one class. Therefore, in fact, this describes the relation between two classes. You just pick up two representatives, one representative from one class, the other from another class. You calculate, and it does not depend upon the choice of the representative. Yeah, so to single out one class, this means to single out such a table of coordinates. This means that x lambda and those gammas are good coordinates in a bundle of frames. So Einstein version of the first law. At each spacetime point, there is a privileged reference frame which we call inertial frame. So mathematically, it is a section of the frame of the bundle of frames, or the frames bundle, and, if you wish, symmetric connection. Now, its coordinate description is just given by those 40 functions. Yeah, whenever we have those 40 functions, we may say that we know the gravitational field.
Any more constraints on these 40 now? Any more
No, no constraints. No constraints. Just 40 without constraints. Yeah, no constraints. So this is precisely the gravitational field of inertial frame. So equations of motion, in particular, if just by chance at some point gamma is equal 0, means that our coordinates are inertial at this particular point, because if it vanishes at one point, it doesn't mean that it vanishes in neighboring point. Yeah, so this is gravitational force, can be eliminated with, so this is what we already know. So Einstein was thinking, roughly speaking, this way, but at that time, the notion of a connection was not well developed. He only had at his disposal the Riemannian geometry, where of course these objects appear, but they are uniquely given by the metric. But till now, I do not need any metric. Yeah. Yeah. What else? Yeah. Typically, inertial coordinates at a point are not inertial unless spacetime is flat in it. So you see that gravity, there are two aspects of gravity: active and passive. Active, how I am coming to the answer to your question yet. The active aspect of gravity, how the gravity acts on moving bodies, is totally described by this gamma. I don't need any metric. But of course, the other aspect is equally interesting, maybe even more, how the heavy bodies produce the gravitational field around that, which means that we would like to know what is the dynamics of this field. So at the moment, if compared with electromagnetism, we would say that we have noticed that the field is described by electric and magnetic field, but still we do not know Maxwell equations, and we would like to recover somehow the dynamics of this field. Now I am going to make a short, yeah, I know that I don't have much time, but let me make a mathematical break here, because this notion of field of inertial frame is worthwhile to understand it a bit more deeply. How to verify that space-time is or is not flat? Suppose somebody brings me a huge piece of paper. When he writes down those 40 functions, extremely complicated, and he claims that this is an example of a non-flat space-time. How to verify? Because maybe it is flat, but only the coordinates which were used are non-inertial. Yeah, if you take just a standard, for instance, three-dimensional Euclidean space, and you write down those gammas in curvilinear system coordinates, for instance, the spherical coordinates, then you obtain a relatively complicated expressions for those gammas. And how to verify whether indeed this complication is due only to the fact that the complicated coordinates have been used. Okay, so let us make such an exercise. Suppose x is not inertial at some point, which means that gamma doesn't zero. Then we may improve them by putting such a quadratic correction to those frames. And you may easily check that this quadratic correction kills gamma at this point. It is just a matter of you see that second derivatives will produce those gamma and so on and so on. And yeah, so this is another very nice interpretation of those gammas. Namely, you may say that gamma, this table of numbers at a point M, describes the necessary quadratic corrections to our system in order to make them inertial. Very nice interpretation. Yeah, so you may see that this is precisely like that. Let me just use always centered coordinates. So instead of x minus m, suppose that m is always 0. You see that the shifting of coordinates does not change those gammas, because gammas are defined by derivatives. So the adding a constant to coordinate doesn't change them. So let me use only centered coordinates, and then this is a very nice formula. Gamma describes this second order correction to our coordinate system, which is necessary to make them inertial. Okay, so this way we see that we are always able to kill gamma at a point, which we knew already from the very beginning. And now, to check whether the space-time is flat in a neighborhood, we would like also to kill it in a neighborhood. But being a physicist, we are pragmatical. Instead of uderzając głową w mur, how to kill it in a neighborhood, let us first try to kill derivatives. We have already killed the value of gamma, so let us try to kill also derivatives of gamma. Yeah, so these are derivatives of gamma. I am used to such a jet inspired notation where derivatives, whenever I have a derivative, so these are coordinates of some space of first jets of sections of some bundle. I will denote this way, that I always add this additional index at the very beginning. So, yeah, so we how to kill those derivatives? By some correction, yeah, by some correction. We see that the zero order correction are irrelevant. We have already discussed. Now, first order corrections, which means that if we perform the linear transformation of coordinates, it doesn't change nothing, because this constant linear matrix will enter here, and here there will be inverse matrix, therefore they will cancel, and so the zero and first order corrections are irrelevant. Now, second order corrections is already fixed, because we have killed gammas and we want it to stay killed. So now, fourth order and higher corrections are also irrelevant. Why? Because gamma contains second derivatives, so derivatives of gamma contain third derivatives. Therefore, if we have fourth order correction after three derivatives, there will remain one x, which vanishes at this point. So again, it will not influence. So we see that only third order corrections do the job. Which job? To kill maybe the first derivatives of gamma. Yeah? Okay, so consider, so this correction has already been done, and we don't move them. This kills gamma at a point, and consider a third order correction. From the very beginning, we can choose those tables which are totally symmetric in these three indices. Why? Because this is symmetric. If W is not symmetric, then only totally symmetric part enters into the game. Because if something is not totally symmetric, it will be killed by, yeah. So from the very beginning, let us assume all the possible third order corrections are correspond to such tables which are totally symmetric here. Okay. It is very, yeah, this correction of coordinates, of course, this we already know, and it is very easy to check because it is just a matter of simple derivative, that the resulting derivatives of gamma will change its value by this V. So you may say, fantastic. Therefore, I will say W in such a way to kill and I am there. No, because W is totally symmetric and gamma is not. Gamma is only symmetric in first two indices, whereas kappa, that means derivatives, is arbitrary. We see that the only thing which we are able to kill is the totally symmetric part. So the totally symmetric part of this table of derivatives of gamma is a gauge parameter because it may be killed by some different choice of coordinates. Yeah, which means that what remains is something which remains forever. If in one system of coordinates you calculate this stuff and you see that it does not vanish, that it means that it will never vanish. And this quantity I have a tendency to call the curvature tensor. The curvature tensor. However, this has already been calculated in an inertial frame, which means in a frame where gamma vanishes. It is very easy to recalculate this to an arbitrary coordinate system. You just add some second order term in gammas, which of course in inertial frame vanishes. And this is a correct definition of the curvature tensor. Yeah. So if it is zero in a neighborhood of M, then it is easy to prove that there is a system of coordinates which is inertial in a neighborhood, which means that gamma vanishes in that neighborhood. This is relatively easy to prove. So, what is this object? This has the following symmetries. First of all, it is symmetric in first two indices, of course, mu nu. Moreover, the totally symmetric part is equal 0. But all of you knows what is a Riemann tensor. Whenever you have gamma, you can construct the Riemann tensor, which is anti-symmetric in second indices, and the totally anti-symmetric part is equal 0. Theorem. Both objects described essentially the same geometric quantity. These are different mathematical representations, or mathematical, it's too much mathematical, just computational representations of the same object, namely of this curvature. How non-flat is the gravitational field? Namely, if you take the Riemann tensor and you take the symmetrization in first two indices, then you end up to constant with my curvature tensor, and vice versa. If you take a Riemann tensor and if you take my curvature tensor and you anti-symmetrize it in the last two indices, then you end up with the Riemann tensor. So this is essentially the same. So these are different representations. R is a very nice object if you understand the curvature as a curvature in a frame of bundles. You take this vector, you transport it parallelly, and you see how it changes. Very nice interpretation. However, the principal fiber bundles are very nice in Young-Mills theory and so on and so on. But the bundle of the tangent bundle is not very general. It is very specific bundle. It has much richer structure. And from this point of view, it is maybe much less natural, whereas my definition is really minimal. Okay. So no metric so far, as I told you, but of course, dynamics of the gravitational field is interesting. Suppose we take this point of view, we are in year 1916, for instance, and we try to understand what would be the dynamics of this matter. So the only way we are able to proceed is to derive it from some simple variational principle. Yeah, this variational principle, if we really treat seriously gammas as a gravitational field.
Excuse me, in this year 1916, variational principles were used.
Yes, they were, because, for instance, the first paper by Hilbert, which appeared, I believe, 5 days before the first paper by Einstein, was already written in terms of a variational principle. Yeah, okay. Okay, but suppose that there is a Lagrangian which depends upon this field and first derivative. However, the theory, the geometric content of the theory should not depend upon the choice of coordinates, which means that probably the dependence upon these things which are not tensors should not be any, but go via a unique combination of them, which is invariant with respect to the choice of coordinates. Moreover, such a Lagrangian density should be a genuine scalar density. Observe that we have no metric tensor to put to first produce a scalar and then multiply it by square root of minus g and be happy that we have produced a Lagrangian. No, yeah, okay. Now, just a mathematical observation. This object splits in a natural way, splits algebraically into three different objects, which, first of all, you may choose a trace, which is just a Ricci. But this Ricci, you are used to the fact that Ricci is symmetric, but at the moment we have no assumptions about the metricity of this connection. Therefore, the Ricci is not necessarily symmetric. It splits again into symmetric and anti-symmetric parts. Therefore, the total curvature splits into three objects, namely symmetric part of Ricci, anti-symmetric part of Ricci, and the remaining part, which I have a tendency to call Weyl tensor, and Jacek always cries that no, because indeed this only when the gamma is metric, then you fulfills all those nice identities, which you know is fulfilled by the Weyl tensor, the Weyl-like tensor, the remaining part. So first we subtract the total trace, and so this is this traceless part, all those traces vanishes, and these two traces. So it splits into three parts. Okay, so if so suppose the God is trying to create the universe, and he thinks which laws of gravity I will give them, which means to us. So the first idea is maybe use only this first part, namely the symmetric part of the Ricci tensor. Therefore, try to construct the Lagrangian, which depends upon. There is not much choice. The only, not only, the Lagrangian, which can be manufactured out of the symmetric tensor, is this and multiplied by a constant. And so let us, and there is no other choice. So it is not just the situation like in general relativity that we can produce millions, billions of Lagrangians out of scalar curvature. No, here the only freedom is this constant. And we will soon understand. Okay, so let us derive Euler-Lagrange equations which from this Lagrange. But because Lagrangian depend on, upon both gammas and their derivatives via this k, it is useful to consider this quantity. Now, the dependence of L upon derivatives of gamma is linear. Therefore, the left-hand side looks like that, whereas the dependence upon curvature upon gamma is quadratic, as you remember. Therefore, after when we derive something like that, then we first take derivatives of L with respect to K times derivative of K with respect to gamma, which is, roughly speaking, gamma, because K depends in a quadratic way upon gamma. So this will be derivatives. So let me denote this quantity by pi, whereas the derivative of L upon gamma is just standard. So the Euler-Lagrange equations look like that on the left-hand side we have derivatives of this pi, whereas on the right-hand side we have this pi times gamma. Now, if you perform this calculation, which is really very easy, then you immediately check that if you put the right-hand side on the left-hand side, this is precisely what we need to upgrade these derivatives into the covariant derivative, covariant with respect to gamma. So this Euler-Lagrange equations means only that this pi is constant with respect to this gamma. Now, let me introduce this notation. Already, Vladimir Alexandrovich Fock in 1938, when he wrote his famous book in General Relativity, which is, by the way, a very good book, he already noticed that all those canonical manipulations in general relativity are much, much easier when we encode the metric tensor not in G with lower indices, but in this contravariant density. Now, my personal modest improvement is that I have put the gravitational, I have integrated the gravitational constant here because it there is a further simplification. Therefore, if having this field of pi, we define the metric this way, this is just maybe, this equation may be a definition of the metric, then conclusion of the Euler-Lagrange equation is that gammas must be a metric connection. So we are almost.
But how do you know that pi is inverted?
No, you have to assume. I'm cheating a little bit. Yes. You have to assume that it is inverted. However, if I have a time during discussion, I will also discuss this point. At the moment, let us assume that it is inverted. So, in general relativity, this is assumed a priori. And now, where are Einstein equations? And they are contained in the definition of this momentum, because you may see this pi is derivative of the Lagrangian with respect to derivatives of gamma, that is canonical momentum, because derivatives of gammas enter in a linear way in the curvature. So we want to decipher this equation. So if you calculate, this is a very simple calculation because the derivatives of the determinant, you have to be able to calculate the derivatives of the determinant. This we are teaching students of the first year at the course of algebra. Finally, we obtained that this object is proportional to that object. Then if you invert, you see that the Ricci is proportional to the metric. If you then translate it into the common language used in gravity textbooks, we see that this is nothing less, nothing more, but the standard general relativity with a cosmological constant. And this cosmological constant enters in a natural way here. No freedom of choice. Jacku, wiem, że muszę kończyć, ale powiedz, jak mężczyzna mężczyźnie, ile minut? 5, dacie 5? Dobrze. Okay. Now, it turns out that the antisymmetric part of the Ricci fulfills a priori Einstein equation. This fact was already known to Weyl, and Weyl proposed to incorporate electromagnetic field into a non-metricity, say, because if the connection is metric, then antisymmetric part of Ricci vanishes, and there is no. Okay. However, it cannot be directly identified with the electromagnetic tensor because physical units do not agree. I skipped this because the discussion of the units is a very important part of that, and I love to discuss that, but within those 5 minutes I have. But in any case, it cannot be like that. However, what about such a Lagrangian? Now, it is okay because both k and phi have the same units. Now, for a very weak field, suppose that this is very small. Therefore, this k prevails, which means that, roughly speaking, it is just the solution of the previous field, and f is small. So if f is very small, then this k is proportional to metric. So roughly speaking, it is maybe well approximated by that. And now we incorporate this cosmological constant here. So finally, when you see something like that, so first of all, this f divided by lambda should be considered as a electromagnetic field, not just f. Yeah. So hence, for a weak field, we let me just skip. I will show you only yeah. So roughly speaking, for weak electromagnetic fields, we have something like that, where f is now this antisymmetric part of the Ricci divided by square root of cosmological constant. If cosmological constant is very big, then we may think that indeed we don't, yeah, so this antisymmetric part of Ricci is electromagnetic field multiplied by something very small. Therefore, indeed, we have a tendency not to feel this antisymmetric part of the Ricci, which means that in a good approximation, the gamma is metric. But it is not. There is small correction. Yeah. Okay. In any case, such a Lagrangian is just a Born-Infeld Lagrangian, where this lambda plays role of the Born-Infeld constant. But of course, God doesn't work this way, and he would probably choose the entire curvature and not only the small pieces. But probably what we see around us is indeed this standard general relativity, where the other fields are very small, and therefore we feel only this standard general relativity, where the metric, where the connection is metric. Other parts of the vanish. Yeah, I think I will skip there. Yeah, in any case, so the God probably, I think so, has used the Lagrangian, which uses the total gamma, the total curvature, or the total Riemann tensor, and out of two reaches, there is only the square root of the determinant of k, which we have used, and there is nothing more which can be used. However, if we want to use the total curvature or the total R, then, for instance, such combination can be used and so on. So in any case, I claim that general relativity, such as we understand it now, is just a theory of this sector. I am almost convinced that the electromagnetic field, such as we know now, is just a theory of this sector. And the fact that we do not use, that we do not see this non-metricity of gamma is something like in hydrodynamics. In hydrodynamics, there is a relation between stress and strain. Strain and stress. In hydrodynamics, the difference of rho minus rho zero and the pressure. However, if the fluid is incompressible, then of course rho is equal to rho zero. However, pi, the pressure, remains as a Lagrangian
Lagrange
multiplier, as a Lagrange multiplier, which means that maybe here we don't see the non-metricity of gamma because it is almost incompressible. In our region of experience, we practically don't see the non-metricity of the tensor, and the electromagnetic field remains decoupled as a Lagrange multiplier. Okay, yes, we will finish. Thank you very much. Excuse me for...
Thank you very much. It's short time for questions. May I refer to your question about magnetism? Yeah, because in some sense, sorry. Ask you about the description of electromagnetic fields acting on bodies, because it should be included here.
No.
Can you explain
Okay, so first of all, this was most of the time I spent for the theory of free gravity. Now, at that stage, some extra matter field can be incorporated, of course. However, the last slide was in the last part of my talk. I tried to convince you that maybe electromagnetism is not an extra matter field which lives aside, but maybe it is also incorporated in the geometry. Maybe this was a great idea by Einstein, who tried to marry gravity and electromagnetism, but on the level of metric. That the idea was that gravity is symmetric object and electromagnetism anti-symmetric. So let us couple them on the level of metric. But this non-symmetric metric is not a nice object. And
let me continue this question. Can you describe electromagnetic field without gravity here? Without gravity, pure electromagnetic field in this approach.
But the entire machinery which I have used was to describe gravity. Without gravity, I just take Jackson and I describe electromagnetic. Of course. So the first who had the idea, so you see, something symmetric with non-symmetric. Einstein tried to marry them on the level of metric. This was not a nice one. Here, we see that you may marry them on the level of curvature, or more precisely on the Ricci, and this looks not bad, I would say. Now, the first who tried to describe electromagnetic field as a non-metricity of the connection was Weyl. However, if you say like that, there is too much freedom. So he tried to fix this freedom, and his idea was the symmetric, that the connection, although non-metric, but at least it preserves the conformal structure. This was just the idea to kill this freedom. But it doesn't work perfectly. Finally, it was abandoned. Here, the theory, once you choose the Lagrangian, the theory is uniquely precise. I don't know.
It would be
I don't know.
something else than.
But of course, I don't know, but it doesn't mean that I haven't thought about it. Of course, I have thought a lot, but it is difficult.
So can I just use the anti-part of this tensor to give a Lagrangian theory? The anti-symmetric part of this tensor. So before you use the
Which part?
Anti-symmetric.
Anti-symmetric change K.
Yeah, anti-symmetric part of the Ricci. I have a tendency to think that it divided by something, so up to some units, and these units, for instance, in an attempt of a toy model, which I have shown you, is provided by the cosmological but maybe it is not, because this was just a toy model, but a very nice toy model. Yeah, where everything. So I have a tendency to think that this antisymmetric part of Ricci describes, up to the choice of units, electromagnetic field. That's all. So let me just say one word. So you see that if you like such an approach to geometry, then you see that there are three different sectors of such a theory. And this one is nothing but gravity. This one, I have a tendency to say that this is probably electromagnetism. And what is the last one? I don't know. Maybe it is just, in fact, I have a tendency to think that this dark matter is there. I have a tendency to see it. We are dark energy, just the energy of dark matter would be here, of course. Yeah.
Can I reformulate this theory just at the beginning, just as a connection theory?
Yes.
That what is given is a connection on the linear boundary.
Yes.
Yeah, and then, but then this connection it has torsion.
Yeah.
No. This one, the way I have defined it, it has no torsion, because from the very beginning it was defined by second derivatives as they are symmetric. Now,
But it is not metric.
no, it is not metric. However, let me only mention that I do not exclude torsion. If somebody of you loves connection with torsion, but the generic non-symmetric connection is not an irreducible object. It splits in a natural way into a symmetric connection and a tensor field. So if you write down any Lagrangian in terms of a non-symmetric connection, I will, for my personal purposes, I will rewrite this in terms of a symmetric object and in terms of this tensor field, which I would, for my personal use, I will call it an extra matter field, which you call it torsion. Yeah. Yeah, because there is always a room for additional matter fields, of course.
Okay.
When you choose the units with the aid of the cosmological constant, can you link the value of the cosmological constant to the difference of scales in the electromagnetic theory and in the gravity?
Yeah, of course. Of course, I would say the following. The toy model of the electromagnetism, and which I have shown you, because if the third part is also used, then of course it will not be related. But this toy model, which I like very much, but I still consider it as a toy model, simply this cosmological constant adjusts the units in such a way that everything, for instance, I showed you that it may be written in a form of the Born-Infeld Lagrangian. Very nice, and the unit of the Born-Infeld constant, which is necessary there, comes from this cosmological unit. Yeah.
So I think there is no more questions, so thank you again.
Thank you very much. Dobrze.
Cześć, do widzenia.
To co?